Hello and welcome to yet another lecture on basic electrical engineering. Paper code E is EE101. Myself, Prathita Roy, Assistant Professor of Dr. Sudhir Chandra Institute of Technology and Sports Complex, Department of Electrical Engineering. Today, my topic is construction and working of DC machines. Lesson objective. After the end of this topic, students will be able to understand the concept of construction and working of DC machines. So, introduction to DC machines. There are two types of DC or called direct current machines. One is the DC generator and another is DC motor. The DC generator that converts mechanical energy into electrical energy, while the DC motor that converts electrical energy into mechanical energy. DC generator is based on the principle that when a conductor is rotated in a constant unidirectional field, a voltage will be induced in the conductor. In other hand, the DC motor is based on the principle that when a current carrying conductor is placed in a magnetic field, a mechanical force is exerted on the conductor. This DC generator operation thus follows the Fleming's right hand rule, while the DC motor operation follows Fleming's left hand rule. So the principal parts of DC machine, next is the principal part of a DC machine. A DC machine has generally three parts that is called magnetic field system. First one. Second one is the armature, and third one is the commutator or and brush gear. Magnetic field system, armature, commutator, and brush gear. So first, we are starting with magnetic field system. Magnetic field system. The magnetic field system is usually the stationary part of the machine. It produces the main magnetic flux. The outer film, that is known as yoke, is a hollow cylinder of cast steel or rolled steel. Even number of poles, that is 2, 4, 6 in this number, are bolted to the yoke. The poles position inwards and they are called salient poles. The purpose of yoke is to support the pole poles and to act as a protective cover to the machine. It also forms a part of magnetic circuit. Each pole core has a pole shoe having a curved surface to support the field cover and to increase the cross-sectional area of the magnetic circuit, reducing its reluctance. The pole cores are made of sheet steel laminations, and these laminations are insulated from each other but riveted together. The poles are laminated to reduce the eddy current loss in the fields. The laminations are insulated from each other but riveted together. Each pole core has one or more field coils, that is known as windings, placed over it and connected in series with another, such that when the current flows through the coils, alternate north and south poles are produced in the direction of rotation. The second is the armature. The rotating part of a DC machine is usually known as armature. The armature consists of a shaft upon which a laminated cylinder called armature core is mounted. The armature core has grooves or called the slots on its outer surface. The laminations are insulated from each other but tightly clamped together. In small machines, the lamination may be keyed directly to the shaft. In large machines, the laminations are mounted on a special frame. The purpose of using lamination is to reduce the eddy current loss in the armature core. Insulated conductors, that is usually made of copper, are placed in the slots of the armature core and are fastened around the core to prevent them flying under centrifugal forces when the armature rotates. The conductors are suitably connected, and this arrangement of conductors is called armature winding. Generally, two types of windings are used. One is known as wave winding and another is known as lap winding. So, what is wave and what is lap winding? In wave winding, the number of parallel paths of the armature winding is 2. And in lap winding, the number of parallel paths is equal to the number of poles. So the third part is commutator and brush gear. So alternating voltage is produced in the coil rotating in a magnetic field. In order to obtain direct current in the external circuit, a commutator is used. In order to obtain direct current in the external circuit, a commutator is used. The commutator that rotates with the armature is made from a number of wedge-shaped hard-turned copper bars or segments insulated from each other as well as from the shaft. The segments form a ring around the shaft of the armature. Each commutator segment is connected to the ends of the armature coil. Current is collected from the armature winding by means of 2 or more carbon brushes that is mounted on the commutator. Each brush that is supported by a metal holder called brush holder. The pressure that exerted by the brushes on the commutator can be adjusted through this brush holder and is maintained at a constant value by means of springs. Current produced in the armature winding is passed to the commutator and then to the external circuit through brushes. So the magnetic flux path in a DC generator, that is the magnetic flux or the magnetic circuit of a 4-pole DC generator, that is shown in this figure. This is the magnetic flux path of a 4-pole DC generator, where the dotted line indicates the magnetic flux path. The dotted line that is indicates the magnetic flux path. This is the EOF that I have already told. This is the armature conductor. This is the flux path. This is the field coil. This is known as pole show. This is the armature, the entire thing, and this is called the armature teeth. So another part in our discussion is the equivalent circuit of a DC machine. In order to obtain the equivalent circuit, we all know that the motor that is converted the electrical energy to mechanical energy, and in case of the generator that converted the mechanical energy to electrical energy, means generator which is moved by some externals, that is called the prime mover. So the armature of a DC generator can be represented by an equivalent circuit. Here E is the generated voltage. So we can say that the armature of a DC generator or a DC machine can be represented by an equivalent electrical circuit, where E, that is the equivalent electrical circuit. This is for the DC generator and this is for the DC motor. So where E, that is, stands for the generated voltage, and RA is the armature resistance, E is the generated voltage, RA is the armature resistance, VB is the brush contact voltage drop. So this is the equivalent circuit of a DC generator, and this is the equivalent circuit of a DC motor, where E is known as back EMF. So what is generator? If I remind the conception of generator, it converts the electrical energy into mechanical energy. That means E minus IARA minus VB equal to V. And this is the conception of DC motor, where DC generator that is converted the electrical energy into mechanical energy, that is known to us. So that is E minus IARA minus VB equal to V. That is the generator where the mechanical energy is converted into electrical energy. That is the electrical energy, the voltage that we have obtained. In case of the generator, mechanical energy is converted to the electrical energy. In case of the motor, electrical energy is converted to the mechanical energy. So that means E equal to V minus IARA minus VB. E equal to V minus IARA minus VB, where E is known as back EMF. So if we remember the working one for the DC generator, where the mechanical energy is converted into electrical energy, and where in case of the DC motor, the electrical energy is converted into the mechanical energy. So in this, after remembering the basic working principle, that is, we can easily able to draw the equivalent circuit of DC generator and DC motor. So we have different types of excitations that is given in the DC machines. In general, that there are two methods of exciting the field windings that we have already seen. The field windings, that is the field coil, and the field windings are excited by two types. One is called the separate excitation and another is called the self-excitation. The separate excitation means that is a separately excited field winding that is consists of several hundred of strands of fine wire and is connected to a separate or external DC source as it is shown in this figure. The figure A, where it is called the separate excitation. The voltage of the external DC source has no relation with the armature voltage, that is, field winding energized from a separate source can be designed for any suitable voltage. Another is called the self-excitation, when the field winding is excited by its own armature. The machine is called self-excited DC machine. In this machine, the field poles must have residual magnetism. The self-excited DC machines can be classified as shunt excitation, that is shown in this figure. Here the field excitation is obtained from the armature voltage. The shunt field excitation, that is called the ampere turns, is obtained by having a large number of field turns with a small field current. For a generator, shunt excitation is a type of self-excitation when the field winding resistance is high but field excitation current is low. Series excitation, that is seen in the figure 1.1c. That is seen in the figure C, that is called this one. Series excitation means the field winding is with a few turns of wire that is low resistance and is excited in series from the armature current. This excitation that is varies with the load current, and the compound excitation, that is both figure D and the D for short shunt and the long shunt. Short shunt and the long short shunt means and the long shunt, where the field winding is given here that if the shunt field is connected in parallel with the armature along the machine is called a short shunt machine. It is a short shunt machine, but the shunt field is connected across the armature. And the if the shunt field is connected in parallel with both armature and the series field, the machine is called long shunt compound machine, that is shown in this figure. If the magnetic flux produced by the shunt field aids the flux produced by the series field, winding the machine is called cumulatively compound. In other hand, if the series field flux, that is oppose the shunt field flux, the machine is said to be differentially compound. Depending upon the number of turns, the series field, three types of compound generators can be obtained. One is called over-compounded generators. The generator voltage increase and the load increase. Level or flat compound generators, the no load voltage is same as that of the full load voltage, and under compound generator, the generated voltage that is decreased and the load increases. Now we will deal with the EMF equation of a DC machine. EMF equation of a DC machine. So As the armature of a DC machine rotates, a voltage that is generated in the coil that we have known. In case of generator, the EMF of rotation that is called ER is called the generated EMF EG or armature EMF, and ER equal to EG. The direction, that is polarity of dynamically induced EMF, can be determined by Fleming right hand rule. In case of the motor, the EMF of rotation, that is ER, is also known as back EMF, EB, or counter EMF, and ER equal to EB. The expression, however, is the same for both the conditions of operation, generating or case of the motoring. Only the polarity is reversed if the rotation of the machine is in the same direction in both the modes. So let us take phi is the useful flux per poles in Webers, where P is the total number of poles, Z are the total number of conductors in armature, N is the speed of rotation of armature in revolutions per second, that is RPS, N is the number of parallel paths in armature between brushes of opposite polarity, and Z by A is the number of armature conductor in series for each parallel path. So since the flux per pole 5 of each conductor cuts a flux of P5, if a conductor moves a 1 revolution, means it is covering the P number of poles. If flux per pole is 5, so the total flux is P into 5. So the generated voltage per conductor, that is flux cut per revolution in Weber divided by time taken for 1 revolution in seconds. So since there are n number of revolutions that we have seen, and n number of revolutions are made in 1 second, so 1 revolution will be made by 1 by n seconds. Therefore, time for 1 revolution of the armature is 1 by n second. It is clear. So the average generated voltage per conductor, that is P5 by 1 by n, that is given by n P5 volt. So if the generated voltage is E, is determined by the number of armature conductors in series in any one path between the brushes. Therefore, the total voltage generated is obtained. There is the multiplication of average voltage per conductor by number of conductor in series path, that is E equal to in P5 into Z by A, that is equal to P5 in Z by 60A, where in, that is in RPM. Previously it was in RPS, so in by 60 is the RPM. So this is called the EMF equation of a DC machine. Next we will come to the type of windings. We have already told that there are 2 types of windings. One is called the lap winding and one is called the wave winding. So the armature coils can be connected to the armatures either by the lap winding or by the wave winding. So let us start with lap winding. So the end of each armature coils are connected to adjacent segments on the commutator, so that the total number of parallel paths, that is A, is equal to the total number of poles. Thus for the lap winding, A equal to P. So the end of each armature coils are connected to adjacent segments on the commutators, so that the total number of parallel paths is equal to total number of poles, that is A equal to P. Wave winding. So in this winding, the ends of each armature coils is connected to the armature segment some distance apart, and only 2 parallel paths are provided between the positive and the negative brushes. Thus for the wave winding, A equal to 2. So in case general, the lap winding is used in low voltage, high current machines, but the And wave winding is used in high voltage, low current machines. Let us take a mathematical problem in order to understand the generated EMF conception and how those two windings are affected the generated voltage. So let a problem that is given the armature of a 4-pole 30-volt wave wound, that is the main thing, wave wound generator has 400 conductors and runs at 400 RPM. It is given in RPM. So calculate the useful flux per 4. So it is P, the 4 pole is given 4, E is given to 30, and the number of conductors, that is 400, that is given because it's wave wound and n equal to 400. So as the number of conductors, that is Z is given 400 and it is wave wound. So number of parallel path A equal to 2 for wave winding. It is clearly seen here. So the number of parallel paths in wave wound A equal to 2. So E equal to P phi n Z by 60. After putting those all values, we will find phi equal to 0.043 Weber. So another problem is given that a 6-pole lap-tuned DC generator has 250 armature conductors, a flux of 0.04 Weber per pole and runs at 1200 RPM. Find the generated EMF. So the number of poles that is given P equal to 6. As the machine that is generally lap-tuned, so number of parallel path equal to number of poles, which is equal to 6. Also the number of armature conductors, that is J is equal to 250. So flux per pole is given 0.04 Weber and speed is given 1200 in RPM. So the generated EMF equal to P phi NZ by 68. So putting all those values, it will be 200 volt. So now another part of our discussion is principle of operation of a DC motor. So when a current carrying conductor is placed in a magnetic field, a force is produced in it. The direction of the force is obtained from Fleming's left hand rule. Let us consider that one such conductor is placed in a slot of the armature and it is acted upon the magnetic field developed from a north pole of the motor. If I apply the Fleming's left hand rule, it can be found that the conductor has a tendency to move to the left hand side from its axis. Since the conductor is in the slot on the circumference of the rotor, the force acts in a tangential direction to the rotor, creating a torque on the rotor. Similar torques will be produced for all the rotor conductors if we assume these conductors are placed in successive slots, the rotor being free to move it and start rotating in the anti-clockwise direction, that is, left hand side of the axis. So previously I have told about the back EMF. So what is back EMF? A question will arise. So when a DC motor armature rotates, its conductor cut the magnetic flux. The EMF of rotation here is the induced in them. In a motor, this EMF of rotation is known as back EMF or counter EMF. The back EMF that opposes the applied voltage. Since the back EMF is induced due to the generator action, its magnitude is therefore obtained from the same expression as that of generated EMF in a DC generator, that is EB equal to P phi NZ by 68, where A is in RPM. EB is the back EMF, that is EB equal to ER. This is the general conception of back EMF. Now we will do with the torque equation of a DC motor. The expression for the torque T is same for the generator and the motor. It can be discussed because the voltage equation for a DC motor is given by, we all know, V equal to EB plus IARA. So after multiplying the both sides, the equation by IA, we can obtain VIA equal to EBIA plus IA square RA. But VIA is the electrical power output to the armature. I square RA is the copper loss in the armature, that is called I square R loss, or the copper loss that is known to us. So input equal to, we all know, that is output plus losses. So that is EBIA, that is the electrical equivalent of gross mechanical power that is developed by the armature. Electromagnetic power, this one. This torque T is the average electromagnetic torque that is developed by the armature in Newton meter. So we all know there is the mechanical power that is developed equal to power, that is the multiplication of angular speed omega into T. So omega equal to, if n is the speed in rps, that is n by 60, so 2 pi n into T. So Pn, that is Eb, that is the mechanical power, that is this is the mechanical power, electrical equivalent of gross mechanical power, EBIA, and this is the copper loss in the armature. So input equal to output plus losses. So the output power EBIA, mechanical power, equal to torque into omega, that is 2 pi n into T. So putting the value of Eb here, that is n p phi nz by A. So it is just putting the value of Eb in this equation. We will get the torque equation, that is torque equal to 0.1595ZIA into P by A Newton meter. This torque equal to EBIA by N by 60. This is called the torque equation of a DC motor. For a given DC, machine, the PZA, that is all are constant. Therefore, the Pz by 2 by A is also a constant that is known to us. So let us, this one is taken as K. So torque is equal to K into IA into phi. So torque is phi into IA. Torque equal to K into phi into IA. So torque is proportional to phi into IA. So we all know 2 pi nt equal to EPIA, that is torque into omega equal to EBIA, or torque equal to 2 pi n EBIA by n Newton meter, and where n is the RPS, so torque equal to 0.159 EBIA n Newton meter, and another part, this one, torque is proportional to phi into IA. Hence, this is called the torque developed by a DC motor is directly proportional to the, that is the torque that is developed by a DC motor, it is directly proportional to the product of flux per pole and armature current. Thank you for listening.